Hey guys, welcome back. Hope you're having a great day. In this video, I'll be covering a term that I've used in this channel in the past, and it's a very common term in mathematics, and that is the term isomorphism or isomorphic. This term is very common because it deals with a very common concept, and that is the concept of sameness. What I mean by that is when we have this mathematical object type, we want to know if we have two of these, when are we going to consider them to be the same mathematical object in some sense? Now, maybe you're an undergraduate math major and you're just coming across this term for the first time in your classes, or maybe you're just curious. Either way, this video is for you. So, isomorphism is a very scary sounding word. It does sound like the name of an alien warrior race, but I'm here to show you that there's absolutely nothing to fear here. We're dealing with the notion of sameness. So let's start from the beginning. Now, I have these two numbers drawn on the board. 6 divided by 2 and 3. They look different, and I used different symbols to express them. But when we're talking about numbers, we're concerned with their value. When we're dealing with arithmetic and counting and anything involving numbers, we're concerned with their value. We are not concerned with how they look. And because of that, we say that these two numbers are equal. We regard them as being the same. Now, here I have these two triangles, triangle A and triangle B. They are the same shape and size. Now, if I regard these two triangles as sets of points on this plane, they are not the same. They are different sets. There are points in this triangle that are not in this triangle. But in the context of geometry, we don't really care that the triangles are located in different places. We care that they're the same shape and size. We regard them as being the same. We say that those two triangles are congruent. So in the context of geometry, our notion of sameness is congruence. There are many different ideas of sameness of mathematical objects. For example, in geometry, we have congruence as the normal notion of sameness, but there's also similarity. That is another notion of sameness. But there are some guidelines that a notion of sameness should follow in order for it to make sense as an idea of sameness. The first requirement is that any object should be the same as itself. A is the same as itself. This is called reflexivity, or the reflexive property. Now, the second requirement of a sameness notion is that if A is the same as B, then B should be the same as A. This is called the symmetric property. And the final requirement is called transitivity. That is, if A is the same as B and B is the same as C, then A should be the same as C. A relation that has all three of these requirements is called an equivalence relation. And any equivalence relation can be regarded as a notion of sameness. It is perfectly qualified to be called so. Now, in some mathematical arena where we're studying some type of object, the default notion of sameness that we use is the one that preserves the properties that we're actually interested in at the time. So, for example, in geometry, we're interested in two objects, their shape and their size. So if two objects have the same shape and size, we regard them as being the same as far as geometry is concerned. Now, when we have these two mathematical objects, a really nice way to talk about whether or not they are equivalent or have that notion of sameness is with functions that preserve those properties that we're interested in at the time. Here are two mathematical objects, A and B. It doesn't matter what they are. They can be shapes, they can be sets, they can be vector spaces, they can be modules, they can be rings, groups, whatever you want. Just some mathematical creature. And we have some notion of sameness on this type of mathematical creature. Now, let's say we have a function from A to B. Let's say f. And f preserves important properties. And f is bijective, so it has an inverse, so we can go back the other way. And we also want the inverse to also preserve those important properties. When this happens, we will regard A and B as being the same. We say A and B are isomorphic, and these functions, either one of them, are isomorphisms. Here's an intuitive example of this that I think demonstrates this idea pretty clearly. So let's say you and I are playing chess somewhere, and halfway through our game, we have to leave. So what we do is we just note where all the pieces are and all the information about the game we've played. Now, sometime later, we're at my house and I take out my Mario themed chess set and I say, hey, let's continue our game. Well, we can continue the game, no problem. The only difference between the two chess sets, the one that I have, my Mario chess set, and the one we had before, is a superficial difference, and it has nothing to do with the actual game of chess. It is outside the scope of the game. So we can continue our game, no problem. We just plug the pieces into the isomorphism that preserves the structure of the game. On the other hand, if I got out my Monopoly board and I said, hey, let's finish our chess game, you'd probably think I was insane. Because those games are completely different. They don't just differ in a superficial way, they have different properties, and those properties that they differ in are relevant to the game. So those two games are not isomorphic. Now, if we want to express our notion of sameness in terms of these bijective, property-preserving functions, these isomorphisms, then we do need to verify that this notion of sameness does meet the three requirements we talked about earlier. So here's what we're saying right now. This is how we state our notion of sameness in terms of these functions, these isomorphisms. We will say that A is the same as B, or A is isomorphic to B, if there is a bijective property-preserving function f from A to B, whose inverse is also property-preserving. So notice that whatever our notion of sameness is, that idea gets captured in whatever property we're asking the function to preserve. Now, we need to make sure that doing things this way and expressing things this way does define an equivalence relation, or those three requirements are met. So the first thing we need to do is verify that for any object A, it is isomorphic to itself. It has to be the same as itself. So we need to find a function that is bijective, property preserving, whose inverse is also property preserving. And that function needs to go from A to itself. So any ideas of a function from A to itself that might preserve some stuff? So the identity function is going to work here. That's always the case. If we just take everything to itself, then we have an isomorphism from A to itself. So A is isomorphic to itself, or A is the same as itself. This function f, the identity function, f of x just goes to x, is a function from A to itself. It's bijective. It preserves everything ever. So that's fine. Now we need to show that if A is the same as B, or A is isomorphic to B, then B is isomorphic to A. So let's draw a diagram for this one. We're assuming that A is isomorphic to B. So there is this property preserving bijective function whose inverse is also property preserving. So this is another easy one. A is isomorphic to B by F, and B is isomorphic to A by F inverse, because F inverse, we ask it to preserve the property in the definition as well. So F inverse is the isomorphism we want to show that B is isomorphic to A. And finally, we need to verify transitivity. We need to show that if A is isomorphic to B and B is isomorphic to C, then A is isomorphic to C. So we'll draw another diagram here. A is isomorphic to B, so I can draw the following, where this function f is a bijective property-preserving function, and so is its inverse. And B is isomorphic to C, so I can write the following, where G is some bijective property-preserving function, whose inverse is also property-preserving from B to C. So I need to show that A is isomorphic to C, so I need a function that preserves the property that is bijective from A to C. So how can I do that? Well, F takes me from A to B, and G takes me from B to C, so all I need to do is compose those two functions. So I can use this one. So that shows that isomorphic is an equivalence relation. It is reflexive, it is symmetric, and it is transitive. So we have verified that this is a valid notion of sameness. Now, to see this idea in action, let's go back to our geometry example with the two triangles. Now, we've established that these two triangles have the same size and shape. If we regard them as sets of points on this plane, well, they aren't the same set, so they're not the same. But they do have the same size and shape, so as far as geometry is concerned, they are the same object. They are congruent, which is the notion of sameness in the field of geometry. So, looking at that in the isomorphic isomorphism point of view, there must be some function, f, that takes the first triangle to the second triangle. F is bijective, and there must be some other function, f inverse, and these functions preserve the shape of a set in this plane. Now, what kind of function is going to preserve the shape and size of a set on this plane? Well, those are going to be the functions that preserve the distance between 2 points. That is, if you have 2 points, x and y, and they're some distance apart, well, then f of x and f of y are the same distance apart as x and y were. So, the isomorphisms of geometry are the bijective functions that preserve the distance between 2 points. Those functions are called isometries. Other examples of this include, if you're currently studying linear algebra, the isomorphisms of vector spaces are the bijective functions that preserve vector addition and scalar multiplication. So if you find one of those from one vector space to another, we regard those two vector spaces as being the same. Maybe the game pieces look different, but the structure is the same. If you're studying abstract algebra and you're learning about groups, the isomorphisms are the bijective functions that preserve the group operation. If you're studying topology, the isomorphisms for topology, which are called homeomorphisms because topologists are strange, those are the bijective continuous functions whose inverses are also continuous. Something interesting is that in topology, you don't always have that the inverse of a morphism is another morphism, but that's for another video. Anyways, I hope you guys found this helpful and enlightening. If you liked the video, be sure to subscribe, and I'll see you guys in the next one.